So now we move on to calculating the noise figure of the EDFA. The noise figure of the EDFA, noise figure of any amplifier, is a ratio of the input SNR to the output SNR. The question is, how do I calculate the input and output SNR? Now input SNR is, so let us just draw the schematic of this. So you have a filter whose bandwidth is, let us say, BO. This is my E in. The output of the filter is what I am calling as E out, and that is what is falling on my detector, direct detection receiver. Okay. One assumption I am going to make here is that we are calculating the noise figure for a short noise limited system, because last time we discussed time and again that the quantum limited noise is a short noise limited system. So we could do this calculation for thermal noise limited system also. The noise in the detector is not because of thermal noise, it is just the quantum limited noise. Under that condition, what is the role of EDFA in degrading the noise figure of the system? Okay. So all these calculations of SNR are done in the short noise limited condition. Now the input SNR is given by, so we are trying, let us say to calculate the input SNR, let us say you have a field E in corresponding to a power P in, and let us say you are putting the detector at the input of your EDFA, right. Assume that you have put your detector at the input of the EDFA. So the current is RD times P in, and SNR is signal power divided by noise power, and signal power is now RD square P in square, and noise power is simply the short noise in the detector. So that is 2Q RD P in delta F, where delta F is the electrical bandwidth now. Why electrical bandwidth? Because now you are talking about the bandwidth of your detector, right. So you will have an optical filter, but finally the short noise is only what is perceived by the detector bandwidth. So that is delta F, where delta F is the detector bandwidth. Now we calculate the SNR out. SNR out is, so you know that if G is a gain of the EDFA, the output power is P out is equal to G times P in. So if you were to write the SNR out in terms of the input power, you say that the output power is RD times G P in the whole square, because the power is G times P in. This is the short noise, and the short noise is again 2Q times, instead of RD P in you would now write G times RD times P in plus the signal ASC beat noise, because that is the additional electrical noise which you had already calculated. It already calculated the power spectral density of that electrical noise corresponding to the beat between the signal and ASC. So if you substitute that, you get 2Q G times RD P in delta F. The power spectral density was this 2 RD square P sig rho ASC. That was a power spectral density, but now that the detector has a bandwidth of delta F, you have to multiply it with delta F. Okay, so we are just borrowing the what we derived for the signal ASC electrical beat noise. Okay, and we know we had derived the power spectral density, multiply it with delta F. Now what is the signal power falling on the receiver? The signal power falling on the receiver is just G times P in. And what is rho ASC? Rho ASC is 2 NSP G minus 1. This we had assumed, or we had just adapted this relation without derivation. So this is the power spectral density of ASC multiplied by delta F. Why are we not considering optical bandwidth here? We are not considering optical bandwidth simply because we have already considered the effect of beat of signal with that of the, so we had already considered the beat of the signal with that of the ASC, and we know that the beat frequency is delta F, which will extend all the way up to BO, but because the detector sees only a beat frequency of corresponding to the detector bandwidth, I will take only detector bandwidth. Remember, this delta f is not the delta f that we had used. I should have used a separate notation. So, I will just say that this delta f is that of the detector, delta f corresponding to detector. So, this delta f is corresponding to delta f corresponding to d. So, I am just putting a suffix d to say that delta f d is actually the detector bandwidth. Instead of delta f, I am putting delta f d as the detector bandwidth to distinguish it from the delta f we used in the previous slide. So, this is all delta f d. Now, there are terms like R D, G, P in common in the numerator and denominator. So, I cancel out these terms. So, G, R D, P in goes off in the first term in the denominator, it goes off in the second term in the denominator, it goes off in the numerator. So, what you would get is R D G P in divided by what remains in the first term is 2q times delta f detector plus 4 R D N S P G minus 1 delta f of the detector. Okay. So, this is my SNR out. I am all equipped to calculate the noise figure. SNR in is R D P in square by 2q R D P in, which is nothing but R D P in divided by 2q delta f detector, and SNR out is what we just had, R D G P in divided by 2q delta f detector this. So, noise figure will be R D P in divided by 2q delta f d multiplied by 2q delta f d plus 4 R D N S P G minus 1 delta f d divided by the whole divided by R D G times P n. I can cancel out this delta f d everywhere. I can cancel out R D P in the numerator. What remains is in the first term you have 2q and 2q getting cancelled, you have just 1 by g in the first term, plus in the second term what I will have is 4 times R D N S P G minus 1 divided by there is a 2q and a g. And remember, your NSP is N2 divided by N1 minus N2. Now, earlier if you remember, when we had derived the responsivity of the detector, we had specifically defined quantum efficiency through responsivity as R D is equal to eta times q divided by h nu. I am missing an h nu. So, 4D NSP h nu. So, the beat term had, there should be a h nu somewhere here, 2 NSP into h nu times g minus 1. So, I missed this h nu. This h nu comes in the PAAC. So, if you go back and look at the power spectral density, it is 2 NSP h nu times g minus 1. So, that term should have, that rho AAC term should have h nu here. So, what I would have is also an h nu here, and q times h nu in the numerator here. So, essentially it will be 1 by g plus 4 R D, this numerator term will have h nu NSP g minus 1 divided by 2q times g. So, of which if I take quantum efficiency as equal to 1, then RD times h nu divided by q, RD times h nu divided by q is 1, because if I take quantum efficiency as 1. So then I can write this RD times h nu as equal to q, and this 4 and 2 cancels. So what I will have is just 1 by g plus 2 NSP g minus 1 divided by g. 2 NSP g minus 1 divided by g plus 1 by g. And for high gain, when g is much larger than 1, g minus 1 by g is equal to 1. 1 by g is a very small number, so I can approximate noise figure as twice NSP. Okay. So this is an interesting result. If your gain is 100, for instance, 20 dB, gain is 100, okay, or gain is 30 dB, gain is 1000, for instance, then g minus 1 by g is almost same, and 1 by g is 1 by 1000 or 1 by 100, which is probably much smaller number when compared to the first term, which means I can approximate noise figure as twice NSP. N2 divided by N2 minus N1 is what my NSP is, and the best possible condition, or the lowest possible value for NSP is going to be 1, and when that's when you have the maximum inversion. Your N1 is 0 and all your ions are in N2. So that's when you have N2 by N2 minus N1 is equal to 1, and when that happens, your noise figure is approximately 2, and corresponding value in dB is 3 dB. So this gives rise to a very important result. However hard you try, you cannot have a EDFA with a noise figure of 0. The minimum noise figure you will have is all 3 dB, because the best NSP or the smallest NSP you will have, spontaneous emission factor you will have, when all the ions are in the excited state. And if that is the case, then if all the ions are in the excited state, N2 by N2 minus N1 is equal to 1, NSP is 1, and if NSP is 1, you will have the noise figure of 2, which corresponds to 3 dB. So the best design of the EDFA will still have a 3 dB noise figure. Okay. Now from this we can actually calculate what is the ASC power, because I know that the power spectral density of ASC is 2 NSP h nu g minus 1, and the noise is typically measured with an optical bandwidth of 0.1 nanometer or 12.5 gigahertz, not terahertz. Sorry, this is wrong. 0.1 nanometer is 12.5 gigahertz. So I can calculate the output noise power. Now remember, this is optical noise power. You can calculate the optical noise power as PASC is equal to it's actually 2 NSP h nu g minus 1 times B optical. Okay. Now B optical as a reference, let us say we are doing a reference of 12.5 gigahertz, optical bandwidth let us say is 12.5 gigahertz. That is the case. If I write everything in logarithm, PASC in dBm is 10 log of twice NSP, that is the first term, then plus 10 log of g minus 1, that is this term, then 10 log of h nu, and then there is a 10 log of 12.5 into 10 power 9. Okay. This 10 power minus 3 in the h nu term is to convert it into dBm. Okay. So this is the optical power, now of which I know what h nu is, it is a constant, I know this is a constant. So this will now be, I know 2 NSP is my noise figure of the amplifier. So, the first term is simply the noise figure of the amplifier, second term is simply the gain 10 log of G minus 1. If it is a high gain system, 10 log of G minus 1 is going to be 10 log of G. See, remember this G is in is not in dB, it is in linear scale. So, in which case 10 log 10 is G. If you take the logarithm of h nu and calculate, it is going to come out as minus 158.92. The logarithm of 12.5 into 10 power 9 and 10 log of that is going to come out as 100.96. So, essentially what you are saying is PAC out in dBm is noise figure in dB plus gain in dB minus 58. This is again a useful relation for design engineers, because if you want to know what is the AC power of the output of the EDFA, if you know the noise figure, if you know the gain of the EDFA, these are two data sheet numbers, right? Noise figure of the EDFA, gain, which is small signal gain where G is very large, minus 58, that number is the AC power at the output of the EDFA, right. So, there is a very useful relation in that sense. I mean, there is nothing new derived here, but it is just that you got it as a very sleek relation which connects the noise figure, gain and the output AC power. Now, what does this optical signal to noise ratio do to your system? So, what happens is the EDFA degrades because of its noise figure. Typical noise figure for an EDFA is not 3 dB, 3 dB is the limit. Typically the EDFAs have a noise figure of about 4 to 5 dB. So, if you have a fiber followed by an EDFA and followed by a fiber followed by an EDFA, this is what happens to the system. So, I am going to mark on top of this spectrum. It has, so the first line that I am marking in red is the input to the EDFA. It has a certain spontaneous emission from the source, which is this floor, and then it has a certain signal power. Now, the ideal output should have been the situation which is shown in the second line. The source spontaneous emission should get multiplied by the gain. So, the floor increases by the factor gain, so does the signal. The signal also increases by the factor gain. So, the source, that is what I am tracing right now. The noise in the source increases by the gain factor. The signal power also increases by the gain factor. This is if the EDFA is ideal, and if it does not, if the noise figure is 1 or if the noise figure is 0 dB. But because the noise figure is not 0 dB, what ends up happening is what I am showing in red again. The signal power remains the same, okay, the gain it just amplifies corresponding to the gain, but the noise is source noise into gain plus the noise added by the EDFA. So, the noise floor changes, the noise floor actually increases. So, even though there is a gain, the peak power of the signal increased, the output signal to noise ratio and the input signal to noise ratio are different. And by how much different? Exactly by how much this EDFA added. So, you have ideally the noise floor should have increased only by the gain factor, but you will see now that it is not increased only by the gain factor, it is increased by this noise figure. Okay. So, this represents, so if you have the signal this like this, so if we want to draw the distance map, which is not shown here, I am drawing it here now. At the input, let us say you have the signal and the SNR is, let us say 30 dB, okay. Let us say the signal power is 0 dBm. So, the noise floor is at minus 30 dBm. let us say it propagates through 100 kilometer of fiber. Now 100 kilometer of fiber would mean 0.2 dB per kilometer. So 0.2 multiplied by 100, so that is 20 dB loss, which means the signal power came down to minus 20 dBm, but the noise power also came down, it went to minus 50 dBm. So the OSNR does not change because the whole spectrum got attenuated. The noise, the optical signal to noise ratio is 30 dB. Now let us say this is fed into the amplifier. So what goes into the amplifier is signal power of minus 20 dBm, noise power of minus, noise floor of minus 50 dBm. Now let us say the amplification is 20 dB. So the signal power goes back to 0 dBm because minus 20 dBm got amplified by 20 dB, you got a 0 dBm. The noise floor should have been amplified to minus 50 plus 20, so it should have been amplified to minus 30 dBm. All what we are saying is that if the noise figure of the EDFA is 5 dB, instead of minus 30 dBm, you will get minus 25 dBm. So that the signal to noise ratio now has become 25 dB instead of 30 dB where you started. Now you keep cascading multiple amplifiers, progressively the signal to noise ratio keeps on reducing. And what is the consequence of reduction of signal to noise ratio? If the signal to noise ratio reduces, your Q factor reduces because sigma naught and sigma 1 increases, so your Q factor reduces, and when your Q factor reduces, your bit error ratio increases. Okay, so that is why it is critical to evaluate what is the degradation in noise figure. But there is one saving grace, it does not reduce by 5 dB in every cascade. You can derive that the noise figure of a cascaded amplifier system is actually the noise figure of the first amplifier plus noise figure of second minus 1 by G1, third minus 1 by G2 plus G1 G2 plus etc. noise figure of n minus 1 by G1 G2 etc. G minus 1. This is a result which is true for electronic amplifiers also, that applies in optical amplifiers also. So if you have one amplifier, the noise figure is just the noise figure of the first amplifier. If you have cascaded amplifiers, the numbers that you are progressively adding will go on reducing. So you need to calculate appropriately. You need to calculate the SNR degradation depending on the number of amplifiers that you have in the system. So that completes the discussion on the signal to noise ratio and the noise figure of the EDFA itself. Now we are all equipped to do a complete link design, and that is what we would do in the next module.